Hello everyone. In this course, we'll discuss topics related to wireless communication systems, mobile communication systems, which will help researchers across the globe to conduct their research. We'll start with the basic concept of multipath fading. So, a wireless channel is one in which the physical medium between the transmitter and the receiver is the free space. The free space uh, takes an electromagnetic wave as the information signal. The signal travels at the speed of light. C is equal to 1 upon square root of mu naught epsilon naught times, where mu naught and epsilon naught are the permeability and permittivity of the free space. When we put that, we take approximately the value of the speed of the signal. C is equal to 3 into 10 raised to the power 8 meters per second. So basically, we consider that the wireless channel is the one in which the EM signal travels at the speed of light. Of course, if the transmitter and receivers are not connected through a wire, the wireless signal can reach to the receiver either in line of sight or in line of sight communication. In line of sight, the signal is reliable. You can understand the transmitter and receiver must see each other, which means there is a direct connectivity in terms of line of sight between the transmitter and the receiver. There is no obstruction. So if there is no obstruction, the signal strength is good, which means that the reliability of the communication system is better. The signal that is received is more reliable. A basic example is satellite communication because you have to put your dish antenna at the roof tower or at any place from where the line of sight communication is there. It can see the satellite and then only the signal can travel in both directions. However, in more dynamic and urban situations, what generally happens is non line of sight communication in which the transmitter and receiver are obstructed. The EM waves then reach in multiple copies, and that gives to the concept of multipath fading. How does what are the phenomena by which the non-line of sight communication takes place? It is basically due to reflection, diffraction, and scattering. When the wavelength of the EM wave is smaller than dimension of obstruction, it becomes reflection. Lambda will be C upon F, where F is the operating frequency, C is the speed of light. So wavelength lambda of the EM wave becomes smaller than dimension of the obstruction, then it becomes reflection, then diffraction. When the signal impinges on the sharp edges of any corner of the table, any corner of the door, then through that also signal comes. That process is called diffraction and scattering when the vice versa of this takes place. So when the wavelength becomes larger than the dimension of the obstruction. So this is how NOS non-line of sight transmission takes place. We basically have a mobile user, so it is generally moving. It will have a direct component if possible, but other than that, all the major components will come after getting reflected, diffracted, or scattering after experiencing certain delays. So this is what leads to the concept of multipath propagation. In multiple copies of the EM waves are received at the signal. We model the system as a linear time invariant system. In linear time invariant system, we have a concept of impulse response. The impulse response is defined as the response of the system when a unit impulse is applied to the input of the signal. So if the copies that are coming after getting reflected, diffracted, and scattered from various obstructions, then what will happen? The energy can neither be created nor be destroyed. So what happens is the original amplitude reduces. So all the signals experience a different amplitude levels AI, which is less than what was transmitted. And of course, when they receive, they are coming from a different path, traveling at a different distances, and therefore they will suffer different delays. We'll talk about the phases later. So ith component of the impulse response is defined as AI delta t minus tau I. But what is the meaning of multipath components? That there are n such copies. So what we will do, we'll mathematically add all those n components. So it's sum I is equal to 1 to m hi of t. And hi of t e is nothing else but ai delta t minus tau I. So we substitute that, and this forms our channel impulse response CIR of a system, which is multipath propagation system. If you are modeling it as a linear time invariant system, we basically are modeling it as an impulse response, taking an input xt and giving an output yt. For an LTI system, the yt is nothing else but time domain convolution of ht and xt. The operation is commutative. We can do first xt and then ht also. So suppose for a multipath propagating signal, we model xt as the input signal, which is the passband representation. So this is real part of xb of t, the baseband symbol multiplied by the carrier, which is e raised to the power j 2 pi fct, where fc is the carrier frequency. E raised to the power j theta is cos theta plus j sin theta. Therefore, the magnitude is the square root of cos square plus sin square, which is 1. And the phase is tan inverse of sin theta upon cos theta, which means tan inverse tan theta, which is theta, which means it just suggests the theta, and the theta is 2 pi fct in this case. Real part of e raised to the power j theta is cos theta, which means it is suggesting cos. So we can understand if the carrier frequency is fc, this is the baseband signal, it is multiplied by the fc, the high frequency thing, and therefore the complete representation is the passband representation. So if this input is multiplied to a multipath ht, output is yt, which will be convolution of h tau and x of t minus tau. We can substitute our expressions for h tau and x of t minus tau, and we'll get this. Here, what we are now intending to is to solve this integral. But you can understand that this integration is a linear thing, and taking real part and summation are interchangeable. So we'll take the real part and its summation outside, and AI has nothing to do with the independent variable of the integral. The integration is with respect to tau, and AI is a constant, so we can take that out also. So basically, we have to solve this thing: x b of t minus tau e raised to the power j 2 pi fc t minus tau delta of tau minus tau I for tau. So you can understand this is the delta signal. There is no integration as such. Integration is nothing else but calculating the area under the curve. So here there is no area. It's basically operating at tau is equal to tau I. We can substitute tau is equal to tau I in the complete expression, and that will yield the output yt. So we can do that, and it will yield yt is equal to real part of summation I is equal to 1 to n ai xb of t minus tau it was. It will now become tau I e raised to the power j 2 pi fc t minus tau I. So now you can understand if I can expand this e raised to the power j 2 pi fc t minus tau I, bases are the same, powers are added, and vice versa is also true. So I will take e raised to the power j 2 pi fct and e raised to the power minus j 2 pi fc tau I, and this can be the complete representation. You can understand tau I is a constant, the delay. So what is happening here? We can illustrate it more significantly. This is a very important equation in which the received signal is real part of summation of I 1 to n ai x b of t minus tau I e raised to the power minus j 2 pi fc tau I e raised to the power j 2 pi fct. The first part is the received signal yt. This ai is nothing else but the attenuated amplitude due to multipath propagation. This is the delayed version of the symbol that was transmitted, and this thing is the phase. What is e raised to the power minus j 2 pi fc tau I? Since tau I is constant, it's not a function of time, and therefore it is just a phase. The phase is minus 2 pi fc tau I, as I described earlier. So this is just the phase shift, and this is the carrier frequency fc. So this component represents the passband representation. How can I again convert it into baseband? You can understand anything except 2 pi fct will become the baseband part. So therefore, what I have written here in terms of blue is the baseband thing, and this is xb of t minus tau I. So you can understand this complete thing is the baseband received signal. So this complete is the baseband received signal underlined by yb of t multiplied by e raised to the power j 2 pi fct. Now we always in research work conduct an approximation where we assume that the channel is narrowband. Narrowband signal means that the symbol bandwidth is smaller than the channel bandwidth. So channel bandwidth is more than the symbol bandwidth. That situation is termed as the flat fading channels. If the symbol bandwidth is less, we can assume that the delay is very small and can be neglected, and we can have xb of t minus tau I as xb of t. And therefore, the received signal can be now written as I from 1 to n summation ai e raised to the power minus j 2 pi fc tau I xb of t. So you can understand. Now, in this expression, the I part is not involved here. I is involved in AI and in tau I. So it's not involved in this part. Therefore, this summation is completely a thing that is separate from xp of t. It's not a function of time. This is said to be the complex wireless fading channel. It is modeled by Rayleigh fading, Rayleigh fading, and this is now modeled as I is equal to 1 to n ai e raised to the power minus j 2 pi fc tau I. So this is our complex fading channel model that we use in all wireless communication systems. And we generate these in MATLAB and Python codes, which are complex in number. You cannot now understand why it is complex in number because of the e raised to the power minus j 2 pi fct. If you consider n number of copies, you can have your own random AI and your random tau I, and the data set can be generated. So this is how we model the narrowband multipath model. That is generally the approximation that we use in any wireless research work. Thank you for watching.